everyone, this video is going to help with exponential functions and basically looking at the transformations of these graphs. Just that's kind of a video that is or a concept that's a little harder to find. So let's look at what an exponential function is and kind of that parent function. So remember, the parent function is just like, what does the general graph look like? And then we do multiply by it and add to it and do different things that kind of change that graph around. So the parent function, excuse me, is going to be something like f of x or y equals b to the x. For anything that you might change around, like you might change it to be a, b, and then you might have like, sorry, I'm totally choking now, x minus h plus k. So the parent function for an exponential is whatever your base is to the value, or to that x is your base or your parent function. And then you can change it by having a number where the a is here, h, or k. So you can put in numbers, different numbers, and that's of course going to change and make your graph look different. But that's kind of what we're going to look at is what are we doing to this, and what do each of those numbers do or move it around. So first thing, the a value, what I times by, is actually going to cause a vertical compression or a vertical stretch. Your book really leaves out the word vertical, and that's kind of important because when you take and look at it in some of the other textbooks, they use horizontal too, and so I want to make sure we use the word vertical even though it's not in your book. So let's look. If a is greater than 1, so that's a here, is greater than 1, then you're going to have a stretch. And again, this is vertical by a factor of a. So the factor, so basically when you times it, it's going to stretch you vertically. So it's going to pull you away from that x-axis by a factor of a. And it, it could be 2 times, 3 times, 4, something like that. If a is greater than, less than -1. Basically, if it has a minus in front of it, it's also going to have a reflection in the x-axis. So it's still going to have that stretch plus, and whatever, it's going to have both of these. A reflection over the x-axis. So x-axis is this way. So normally you're going to have some kind of graph up this way. If you have a negative on that a, it's going to flip it over and make it go like this way for your graph. So it flips it over when it's negative. But it also will have that stretch if that number is less than -1. So it could be -2, -3, -4. If it's -1, notice there's no equal on there. You don't have a stretch. Or if it's just 1 on the at all, if there's just there's no a number, it's just a 1, then you don't have a stretch at all. But the stretch is there whether it's negative or positive. But then you add that reflection. Okay, so what another thing with a? If a is between 0 and 1, that makes it a fraction, right? So if it's 1/2, 1/4, 0.26, something like that, what it's going to do is it's going to compress or smush you vertically, and by a factor of whatever the a is as well, whatever the fraction is. So this is a compression, and again, it's vertical, and by a factor of a. All right, and then if it's negative, same kind of idea as before. If it's negative, it has the compression still, but it also has a reflection um, over the x-axis. So if it's negative, it has that reflection period, no matter if it's a fraction or a whole number. Remember, whole number, big numbers, bigger than 1, make a stretch, and a number that's a fraction or a decimal, smaller than 1, right, whether it's negative or positive, are going to do the compression. Okay, so smush, stretch on our graphs. All right, so let's look at what H and K do. So what H is going to do is it's going to have a horizontal translation. It's going to move you back and forth. So H is a horizontal translation. So it moves to left and right. So here's my side note. The negative sign here is going to move you to the right. And then positive H moves to the left. So it's kind of opposite of what you think. It's always that way with the parent function or the transformations. It's always whatever's by the x, no matter if it's an x, when we're looking at those x squareds or this one, whatever you do here, a negative moves you to the right and a positive moves you to the left. So it's always the opposite of what you think it should be. And they also call these a horizontal translation. So I have to cheat with how to spell some of these words because I am not a good speller. So horizontal translation is what that's called. So K is going to move you to the up and down. Or it's called a vertical translation. Okay, and this one's not tricky. If it's positive, it moves you up. So positive moves up. Moves up, and negative moves down. It's not the opposite with the K. So anything you add to the side, it's like I'm going to do this all, and then I'm going to add something and move it down, or add something and move it up. So that's kind of not add. I guess it'd be subtract down, add up. Those are kind of your general rules. And these rules you will see over and over and over as every type of function we look at. You have this general idea of a function and you do different things to it to move it around and to change it. So you should sort of be getting good at these translations, compressions, stretches, and all that kind of stuff. So let's look at a couple examples, and we will look at these on a graphing calculator as well as just looking at the equations. So here's my first example. What if I just have y equals 3 times 2 to the x plus 1? Okay, so if I just have it could have been f of x, right? So same thing. What would this look like with a graph, and what is the parent function? So I'm going to scoot over in front of my thing here and show you on a graph. Ignore what's graphed there. It was another one I was looking at. So let's look at what we have, which is 3, and then here's the times 2 to the power of x, and then we have to do a plus 1. Okay, and then what would be the parent function of this? So the parent function is going to be just 2 to the x. So you take off the number you're timesing, which is our factor, and we're taking off the plus 1. So we're going to look at just 2 to the x power, and let's graph these. So the first one's red, second one's green. And again, this is just that free calculator. It's the Holt version from last year's curriculum, but we can access for free, and if you don't have a graphing one by hand. If you're doing it by hand on like a TI, you just hit y equals and put them in, and you should be able to see them. So let's look, first of all, here's our parent function. It's green, right? And we can see that we have moved this one up. And we can also see that it's kind of like stretched up faster, right? It's going up faster. It's pushing away from the x-axis. So it has a stretch there. So if we look, it has a 3 in front, which we said if it's greater than 1, it's a stretch by a factor of 3. So we have a stretch by the factor of 3, and the 1 is going to move you up 1. We didn't have a number by the x, so it didn't move back or forth. So we stretched it up plus moved it up 1. So it kind of looks like you moved up more than 1, mostly because of that 3. So we really moved it up by 1 times 3, or 3 times here. So that's kind of the reason it's more than just a 1 up kind of thing. So that's kind of tricky with the times. But you can get the idea from a graph, and you can also list your transformations on the piece of paper. So we know it is going to have a stretch by 3, and that's your factor. And then it's going to move, it has a vertical translation of 1. Okay, so that's kind of the listing of them. So we stretched by 3 and we translated it up 1. Oops, yeah, I wrote vertical. Okay, it's like, oops, I don't have the word up in there. So that's kind of how you look at those. Let's look at one that has a little bit more things on it. And again, I could write f of x, doesn't matter. If it's a y, f of x, same thing. So what if we have 3 to the x plus 1 minus 5? So this has got a number in all those spots that change it up and threw a negative in front. So let's just think it through. -2. Okay, negative will reflect you over the x. The 2 is going to be a factor of 2, and it is still a stretch. I should have done a compression, but oh well. It's another stretch. And then up here, this number doesn't matter. That just means our base or our parent. Up here, we have a plus 1, which is the same as saying we are moving to the left 1, because it's the opposite, right? And then this one will move us down 5. So let's look at the graph of that. And I will just use the same online calculator because it's a little easier for you to see. Okay, so this one is -2. I'll just use a parenthesis. It doesn't really matter. 3 shift to the power of, and then I'm going to use a parenthesis again for the x plus 1, and you have to on all calculators for that, because otherwise it'll only take you to the power of x and then plus 1. You have to have that saying that whole thing is your exponent, and then we have a -5. Over here, what's our parent function on this one? Well, our base is 3, so the 2, the 1, and the 5 are all numbers we added. So the base is just 3 to the x. Let's graph those. We got our red. Oh, he went off because we would have to move up to see. Where can we make the zoom out? I was like, I need the red to show up. Where is he? Maybe I need a time symbol in here. Ah! So that might have taken you a while to figure out. I was like, no, it shouldn't be that far down. I should be able to see it at the zoom out. So zoom in, zoom out on this one. Same with your windows on your calculator. That's how you can zoom in, zoom out, even though it has a zoom word. The windows, you make them bigger. So instead of just going to 10, maybe to 20. All right, so let's look at our differences. Here's our general one. What did we do with this one? We flipped it, right? And that was the negative. And then the 2 kind of made it go, well, 2 times -5, it moved it down to -10, if you can see that, where it crosses, because you're changing it, you're upping it by a factor of 2, plus you -5 down, so it kind of went way more down. And then the plus 1 is going to move you 1 this way. Okay, so you can kind of see that. I think it's easier to see it in the numbers than it is to see necessarily just looking at the graph and seeing what the changes are. But this is the main idea that you need to get from this section. I do have, if you see an E, so I have a couple things I want to make sure I point out. If you see an E on any of your problems, E is just a number like pi, and it's on your calculators as e to the x, or that's just, here it is, e to the x on this one here. So you're always taking e to some power usually. E is what allows us to calculate like interest that's compounding all the time or bacteria that's growing all the time. So now that we're starting to get exponential word problems, you're going to see E in some of them. Don't think it's tricky. You have to use your calculator for E, and it's just a number like 2.7 something. But let's look at a word problem. Hopefully we can read my word problem straight off here because I don't really want to write it up. It was really super duper long. I could probably get it out of the book, but this, anyway, is kind of a long problem. But the half-life of a radioactive substance is the time it takes for half of the material to decay. We're looking at half of the material to decay away. Phosphorus 32, which is just the name of this thing. The 32 is a little tricky because it's a number, is used to study a plant's use of fertilizer. It has a half-life of 14.3 days. Write the exponential decay function for a 50 milligram sample. Find the amount of phosphorus 32 remaining after 84 days. So let's break this down. First of all, decay and growth. That number that's your base of your exponent, if it is a whole number, then you're growing. If it's a fraction, then you're going down. So decaying has a fraction in that place where, like we had a 3 in the last one, 3 to the x, that would be like 1/3, and it would be decaying. It means it's going to be going down instead of up on your graph. So this thing has got a half-life, so it's cutting half each time, each day, I think is what this one is referring to. So let's look at how we should write this formula. We want the half to be our base. So our base function for this is going to have the 1/2 to the x power. So I already have the other numbers in, but that's okay. So let's go through how I found the other ones. The other one is it has a half-life of 14.3 days. That is a little bit tricky. Time days is always up here. We don't know how many days for the formula we want it to be any day. We know we're going to find it for 84 days on the second one, but we want to be able to have a function for any day that we put it in. So the tricky part is knowing it's 1 over 14.3 days because it's you're going down that each time. It's a little tricky. And then the 50 is referring to our sample has got 50 milligrams. Okay, that's always your starting. How much you have always goes in front. From here, this is the first answer. That would be our equation. So again, we're going down by half. We're going down by, or we had the half-life of 14.3 days. And then we're going to go with putting an 84 in for days for the second question that it asks us. And you put this in your calculator. So be careful how you put that in your calculator because that's probably what most people will do wrong and get the question wrong. So let's clear this and go into the regular calculator. You have to put in the 50. I have to like kind of hold this up a little so you can actually see what I'm typing. And then you're going to put in exactly like you see. I can use 0.5 for 1/2. I can use 1 divided by 2, whatever. To the power of, again, you have to do a parenthesis. 1 divided by 14.3. And I want to times that by 84, end your parentheses. That's all the exponent. And then hit enter. And that's how I got 85 milligrams. Okay. This question was a little tricky. That's why I picked it. And that's why I showed it. It's not necessarily what you'll see exactly, but I still wanted to try one word problem. So you're looking at those changes in those exponential functions mostly for this chapter, but you also might look at one and be told, well, is it growing? Is it decaying? So look at that base number for if it's growing or decaying, and then you should be able to, each word problem will be different. You might have to look at the example for them, but let me look real quick to show you. So if I had this, is that growing or decaying? It doesn't matter if I have another numbers. That one has the base of 1/3, so it's a decaying problem, right? Versus if I would have had something like we were graphing 4 to the x. This one is a growth decay. Lots of things decay, lots of things grow exponentially. It means they go really, 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 really fast. So, um, and you use this a lot in financial things as well. So, anyway, hopefully you found this video helpful.